everybody. Today in our new weekly episode we are going to talk about the well-known Planck constant. It can seem a little bit strange to study such a rather rarefied concept compared to the basics such as the speed of light or the force of gravity, but it plays a major role in understanding the behavior of matter at a subatomic level. To clarify this complicated world, we can say that the subatomic scale is a domain of physical size that contains objects smaller than the atom, such as the electron, protons, or neutrons. First of all, who is Mr. Planck, who gave his name to this constant? This German physicist, called Max Karl Planck, lived between the 19th and 20th century. He studied for more than 20 years the problem of black bodies' radiation and discovered, while studying it, the famous constant. He was awarded the Nobel Prize in Physics in 1918 for his work. This constant tells us about the energy of individual photons related to the wavelength of their radiation. We are now going to see and explain the Planck relation. So, as you can see, E is the energy, c the velocity of light, lambda the wavelength of the light, and finally h is the Planck constant. He made this equation after he found that the energy of a single photon was proportional to v, the frequency. So he combined his formula E equals h times v with v equals c divided by lambda. Finally, we are now going to explain our experimental work. So we used LEDs in this experiment because each LED has a different threshold at which electrons start being produced. Measuring this voltage and knowing the values of emission wavelengths can give us a path to find the Planck constant. We did the electrical circuit using equipment we had in our school. So we had 6 LEDs, one red, orange and green, and white, a blue and a yellow one, to make our results as accurate as possible. And also a generator, a resistance, a rheostat, and 2 multimeters. The resistance is in the circuit to limit the quantity of energy. The rheostat has the same function except that it has a rotation center so that the voltage can be adjusted. One multimeter measures the tension, the other one the intensity of each LED. We tried for many values thanks to the rheostat, which can change the tension easily. We noted down each value for each LED and in an Excel table, as you can see now. After that, using the measurements, we made for each LED the graph of the voltage in function of the intensity. Then we created the tangent of each curve. The values are not very precise, but we did our best. In the threshold, we extended the tangent so that it could cross the x-axis. So it is the intersection between the tangent and the horizontal axis. It is also called activation voltage. Using a spectrometer, we measured the wavelengths of all LEDs. Thanks to a software, we could read on a graph for which wavelength the intensity was the biggest. The graph in the middle helped us to determine the wavelengths. We made such a graph for each LED. After that, we have to make the graph of the activation voltage against the inverse of the wavelength. The Planck constant can be calculated from the gradient of this line. The coefficient of the slope is 1.8 times 10 to the power minus 6 volt per meter. We all know that the slope is equal to the h times c divided by e, so we solve this equation. The equation to calculate the Planck constant is h equals E times m divided by c, where E is the charge on the electron in Coulomb, who is a constant. C is also a constant. It is the speed of light in meter per second. M is the slope in volt per meter, and h is in joules per second. After the digital application, we determined that h was equal to 9.6 times 10 to the power minus 34 joules per second. The results are far from the real value due to the instrument, the rounded values given by the software, and maybe the bad measurements. we can calculate the uncertainty. So we found out it is 45%. The result can seem a bit high, but each value can impact the final value by a lot. So, for example, if we took the white lead away, the whole result would change. So I think our result isn't absurd, but it's just not precise enough. Thanks for watching. See you soon for another episode.